Like you well said, I'm a researcher up in Umeå, Department of Forest Ecology and Management. We have a small research group here that are working on trees and the benefits of how we can use trees better for benefits for people, especially in poor tropical countries. So we call ourselves sometimes the Trees for Life Lab, and this presentation is based on work that I have done with a lot of people, more than I can present here. It's also organizations like C4, ECRAF, INERA in Burkina Faso, and SLU of course. And most of the slides and pictures I show here are made by myself or Ida Bargustubella, so I would like to acknowledge that already here from the start. And the title then, how to increase carbon and groundwater with trees. It's a question, and some of the, I will hopefully provide some more insight into this towards the end of the presentation. So there are more people than me that are interested in trees and the benefits that we can get from trees. There is a lot of initiatives the recent years for restoration work and using trees for carbon sequestration, for other benefits to livelihoods, as forage for animals, to improve soil fertility, and so on. This is one example from Niger of an area that have where one has increased the number of trees in an area through projects and through the work of local farmers in the area to protect trees. But one question here is then, what is the impact of these trees on and the increased tree cover on water availability? And if we ask around and look for this, there is usually tree planting organizations are thinking that this benefits the water availability, and you can increase water flows in the streams, especially during dry seasons, and it benefits the water levels in the wells. And this on top of the other benefits like carbon sequestration that we have from trees. The carbon benefit, the carbon sequestration of the trees is rather well documented. There are lots of sources, and depending on the situation and this type of system, we get the carbon benefit with the trees. So this is sort of the only part of carbon. It's not disputed at all. We have carbon sequestration, more or less depending on the situation. So we could basically simplify the pattern with tree cover and carbon stock by saying that if we improve the tree cover, we improve the carbon stock. But if we're changing then to groundwater recharge, the other part of this presentation that will be the main part of the presentation, then we have rather diverging views on what will happen. So we have a long history of tree planting organizations, environmental organizations, foresters that are saying that we have a linear response. When we have more tree cover, the benefits to groundwater and dry season flows, stream flows are increasing. On the other hand, we have people, scientists, hydrologists that have for a long time been saying that this is not what happens when we are looking in our streams. Then we see that the more trees we have, the less water we have in the streams. So this debate has then been going on for centuries. And there's been sort of no real progress in this. Until I would say a science publication came out some time ago now, which were quite influential. And one of the authors of this publication, in an interview afterwards, he said this, that it doesn't matter where you are in the world, if you grow trees on croplands, you use more water, and this is harmful. It reduces available drinking and irrigation and harm local aquatic ecosystems. And this publication, if you go into a little bit more of the details, they say they investigated more than 500 forestation studies, where they also had catchment data, water data from these forestation studies. And the conclusion was that 30–40% of the stream flow in those catchment were lost after these forestations. And this was proportionally more in drier areas, and also, which was important in this publication, was that they looked at dry season flows. So, and they said that this was even larger reductions in the dry seasons than the total yearly reductions in stream flow runoff. So after this publication, there were a lot of policy briefs, lots of information, such as this one, where one now finally could say that we can replace the old myths with scientific evidence. And this policy, and this reached up all the way to the policy organizations such as FAO, that in their reports and their recommendations, they were saying things like this, that there is no question that even partial forest removal increased downstream water yields. And even further than that, even dry season flows are also reduced as much or more. Even if they said also that in theory, it's still possible that when you have more trees on degraded agricultural land, then it could in theory still be the case that you can get increased dry season flows because of improved infiltration of rainwater into the soils and groundwater. But what they are saying then is that we have rarely been seeing this. There is no evidence for that this could happen. So this was the situation a few years back when I started working with these issues inside an organization called CFOREST, Center for International Forestry Research. So I started to work with the trees and water, and we're going to make reviews on this issue. And my job was to basically summarize this and make a review of the review and publish it. But then when I looked into these papers, these science papers, and I looked at the supplementary information, I started to realize that actually the evidence might not be as global and as wide-ranging as it looked like. So these 506 observations that they talked about, that they made regressions of, were actually only 17 locations in the world. And 3 of them only were in tropical countries. None of them were on such degraded sites that where one could expect, for example, dry season flows to be improved. None of the studies or the locations were in the drier parts of the tropics. And all of these, except 3 of the 70 locations, were planted with eucalypt or pine plantations. So basically what they are, the results are valid for are catchments with more or less plantations, area covered by plantations. And in contrast, when I looked at tropical countries where I have visited, it looked more like this. So we have not plantations, but rather more or less tree cover. We have some areas that have more closed canopies, but most often, very often, we have scattered trees. We have agriculture, we have grazing lands, we have more or less open tree cover. And as I could see it, the evidence that we had did not cover these situations. So then I started asking myself, so how much is this really? What is my impression correct that most of the land we are talking about in Africa and other tropical countries are not these plantations? So I looked at the literature, and now this is starting to get a little bit old, but still I think the proportions are more or less valid. We can see that plantations are only a little fraction of the total forest in Africa. I think if you look at it now, it might be 14 million hectares of plantations, according to FAO, in Africa. And we have closed forests, which actually might not be as closed, all of it, because it's the definition of closed forest in FAO is 40% tree cover. So much of this, what is termed closed forest, is actually rather open forest as well. And the majority of the forest or tree covered land is more open, fragmented, or other wooded lands. And then on top of this is probably agricultural land that are not at all included into these definitions. So then I started to think about what can we do then to find out if this is important, if this extra infiltration that we might get from trees because we are improving soil infiltration capacity, the ability of water to enter the soils and reach the groundwater. If we have situations like here, like the picture you see from here in Burkina Faso, where we have dry forests that are thinned out, cultivated, and we get the agroforestry system that is called agroforestry parklands in this region. So when we think about this is still Burkina Faso and agroforestry parkland. We need to think about the relationship between this infiltration capacity and the rainfall intensity. So we know that in the tropics, in contrast to northern temperate and boreal areas, we have rainfalls with 10 times the erosivity than we have in northern systems. We can have 30–40% of the yearly rainfall coming with rainfall intensities that are more than 30–40 millimeters per hour. And then we get situations like this where we have surface runoff. So then the infiltration capacity, the ability of the soil to receive this water gets more important than in temperate areas. So what I started to do was to look at literature, and we did a meta-analysis on what is the effect of trees in forest and in agroforest on the infiltration capacity or infiltrability, which is synonymous with infiltration capacity. And the conclusion is that these studies that have been done, they indicate that it's about 2 to 5 times more infiltrability when we put trees on the land than if we have agriculture without trees. And if I would summarize this is a conceptual figure, and based on sort of these reviews that I did. So it's a rough picture, but what I'm trying to say here is that if we increase the tree cover, we go from lower infiltrability to higher infiltrability in forest. And in between them, the tree-less areas and the forest, we have areas with more or less trees. And we have areas with larger gaps and smaller gaps. And when we are close to trees, like here, then we have higher infiltration capacity. And if we are far away from trees, then we have lower infiltration capacity. And these infiltration capacities, the lower one, where we don't have the trees, they are often lower than the rainfall intensities that we have. So this is the general pictures from the literature that I reviewed. So then we started to see, can we find representative areas of this And we went back to then Burkina Faso and these agroforestry parklands. And when we measured in our parkland, we saw the same pictures as we had seen in the reviews. So close to trees, we had higher infiltrability, and far away from trees, we had lower infiltrability, the median below 10 millimeter per hour in infiltrability. So much lower than the general rainfall intensities. And the difference here is about 4 or 5 times, just like this picture we got from the reviews. So then what we started to think about, how can this work spatially then with the water balance. So the water balance consists of, and I should say, the soil water balance and the groundwater balance. So then it consists of water that is lost from the trees through transpiration and interception, and then also water that enters then the soil through the infiltration, and water that is lost cannot enter because of too low infiltration capacity and is lost by surface runoff. So then when we have full cover of trees, or we are under the trees, then we have little water entering the soil and the groundwater, because it's intercepted by the tree canopies and taken up by tree roots. If we have large gaps, we could also have low groundwater recharge, because instead we have loss through surface runoff. While we were thinking that in the small gaps, then we have less interception and transpiration, we have better infiltration capacity, little surface runoff, and therefore the most groundwater recharge. So this was the idea, and we went out to try to test if that would be the case. So what we did was to dig pits around in the landscape. We did it under trees, in small gaps, and in large gaps. And we then collected soil water at the bottom of these pits, 1.5 meters below the soil surface. And we also measured how much these trees were using, water they were using with subflow measurements. And the pattern that we got was that so if you look at this picture, this is summarizing sort of how far this measurement were from a tree trunk. And then on the y-axis, it is how much water has reached this collection point, 1.5 meters down in the soil. How large percentage of the rainfall over a year that reached there. So the percentage of the yearly rainfall. And what we could see is we could not find, or very little water under the tree trunk or under the tree canopies. But as soon as we got away from the canopy, on the edge of the canopy, then we were able to collect quite large amount of the rainfall down 1 meter down in the soil. But then when we came far from the closest tree, out in the big openings, then we lost again water. So we had less water down in the soil. So then this gives us a rather complex spatial problem. So how does this then translate over space? So what we did was to try to model this. So what you see here in 2 dimensions are sort of modeling experiments where we put trees, different number of trees, and the trees now here you can see as black dots because there were no water coming down. So black is no water or little water, and white here is more water, and then the more dark red is then less and less water. And then we increase the number of trees, and what we then see is that the more trees we have, the more areas of this white maximum recharge areas do we have, until we reach a certain point where we get so much of the black low recharge areas under the trees. So then it starts to decrease again, the recharge at 1.5 meter. So if we then put this in a figure where we have canopy cover, what we see is a pattern where if we are increasing, the more trees we have, we reach a maximum and then it decreases again. So the different lines here are representing different scenarios. The top one is if all the water that the trees use is coming from above 1.5 meters, and the bottom one is if all the water they use are coming from below 1.5 meters. And we have done some tracing studies, and what we can conclude from those tracing studies is that in reality it is of course somewhere in between those extremes. So we have something like this, most likely going down to the groundwater. So we have increasing, the more trees we have, the more groundwater recharge we have, and then it decreases again. If we look at this collection points, the recharge that we collected in small and large gaps only, we exclude the under canopy areas. And then we looked at how much are we getting in recharge depending on the rainfall intensity during the day. So we divided it up in small rainfalls, medium rainfalls, 10 to 20 millimeters, and more than 20 millimeters. And then what we saw was that, of course, this recharge that we see is mainly coming during the large rainfalls. And interestingly, then the small gaps, gaps that are around 10, 15 meters between trees, they have enormous amount of more water coming down into the deep soil than in the treeless, more large gaps, 30, 40 meters from any tree. So it's more than 10 times the amount of water is coming in the small gaps. So then, since we are scientists, most of us here, I think, why is this? We wanted to find out what is the reason for this. So we did tracing studies, both with isotopes and with colored water. to see how is the water flowing through the soils in these different areas. And what we saw was that here is again we have sorted the measurements according to the distance to the nearest tree, is that we have what is called preferential flow when we are close to trees. So this means that water are moving in cracks or channels, large pores in the soil, rather than uniformly through the soil when we are close to trees, rather than further away from trees. And if we look at this picture, which I think is an illustration of what is happening here, is that the influence of the trees in the soil is much more wider than the canopies might indicate. So the roots are stretching away out in these openings, 10, 15, 20 meters away from the trees, and then are influencing the soils around. And also they are attracting soil animals, termites mostly in this case, but also other animals. So around the trees that we have this, the water is moving through channels made by these animals, these termites. So what is happening, we believe, is that that trees sort of give the water a line, a preferential flow path is one term for it, through the soil. And that is done through tree roots, channels, and the soil macrofauna. And this prevents the soils from flowing on the soil surface, being lost on the soil surface, but it also make the water escape and getting stuck in the soil surface and then being exposed to surface evaporation. So if we're summarizing this, we can say that, well, we don't have this linear increase with tree canopy cover. Instead, we might have two situations. In many situations, like in temperate areas, in boreal areas, we do have a decrease in groundwater recharge the more trees we have. We can also have it in tropical countries where we have sandy soils or maybe volcanic soils that are not affected by trees, or the infiltration capacity is large enough so that anyway, with or without trees. So there are such soils. But many soils, these alphisols, ultisols, that are prone to soil erosion, then we might have this situation instead, where we have an intermediate tree cover that is the best for the groundwater recharge. And the interesting thing then, I think, which is also part of what I want to emphasize here, is that we can do a lot of things now. Suddenly people have not been talking about what we can do for improving groundwater recharge, what kind of management options we have. It has kind of been lost in the scientific work because we have been thinking that tree cover is then the trees are always detrimental for groundwater recharge. But actually, we can do a lot of things more that can improve this even further. So like pruning the trees would reduce the water loss. If the more small gaps we can create, the more infiltration we get, and we can look at species selection, the species that use less water, and also all the trees are using less water, and other soil improvement techniques could also help changing the pattern of this curve so that we get higher groundwater recharge and the optimum tree cover where the tree cover where we have the optimum recharge is also changed to a higher tree cover. And the interesting thing is also that I think that even if you're skeptic to this idea of the optimum, we can also improve sort of in these situations where we have a linear decrease with tree cover. All these management options would also increase the groundwater recharge. So if we look at the agroforestry as an example, there is a lot of things that we could do to improve groundwater recharge if we were thinking about it. But as far as I can see, there is nothing in the literature that really discusses this or shows what should we do to get a better groundwater recharge if we are having agroforestry. And the same actually applies also to forestry in natural forest or in plantations. So that's why we are starting experiments in this case in Rwanda, where we are looking at species effects and also distances between rows in agroforestry and various gap sizes, you could say, in this agroforestry system, to see if we can learn more about the groundwater recharge effects and the water use efficiencies in these systems. So if someone gets interested, have ideas about this, please join us, because I think there are too few people working with these issues out there. So the final conclusion, last slide, then, is that I believe there is a lot of opportunities for improving groundwater recharge in water limited areas. And there are a lot of things we could look at, how we distribute trees, how trees are distributed, which tree species we are favoring, the age of the trees, tree pruning activities, and livestock that is often an integrated part of these systems. They all affect the water budget and then the groundwater recharge that is a result of this. So that is what I wanted to say. It's the end of my presentation.